Um, okay, so really quick, this is gonna have to be the quickest lecture I've ever done, because I just have something that I needed to leave to. It was already planned. So you'll notice I'm in a different room, the room that I've been using for a couple years now, basically, or for at least a year and a half. Not only that room, but all the rooms on the bottom floor where I'd normally do this recording. They, what do you call it? They knew this was coming, but they basically took down those rooms so they could do some renovation on the building. So I was freaking out there for a second because I honestly didn't have a room to do this video in. But I found this one. But because of that, I have a lot less time than I was expecting for this. So we're gonna do this, like I said, this amalgamation video from 9.3 to 9.6. Very quick. You'll kind of see I'm just gonna hit kind of the main points of these four sections, and then just an example or two per point. But you'll also see that it at least works well for these four sections. So everything we're gonna talk about, everything in chapter 9 is actually just about the same thing, just different ways to test for the same thing. So anyways, so let me get some more lights on and let's get going. All right, and I will, hold on, where's the thing? Oh, come on, thing. It's like, let's try this. Let's switch to here. Let's see if it'll. I think it just needs to catch my form. There we go. Yeah. All right. Sweet. All right. All right. So what we're going to look at for these four sections. So right at the end of the last bit that we learned about basically convergent and divergent, what do you call it? Convergent and divergent integrals. And so we're going to use that idea as kind of our launching point for what are called convergent and divergent sequences. So we're going to look at sequences of numbers, sorry, convergent and divergent series, really. We're going to look at what do you call it? Sequences of numbers, and we're going to add them all up. And the question is, do they converge or do they diverge? Do they end up at a single value, or do they tail off forever and never add up to anything? So let me find an example from the book really quick. Start our way there. All right, so this is out of section 9.3. I'm looking at exercise 3. So just so you kind of know where I'm looking at. So I'm looking at exercise 3 and exercise 3. The sum n equals 1 to infinity of fractions of this form, 1 over n plus 3. And is it 0 or is it 1 that we're starting with? Now, just to remind you, so series and sequences you, again, should have already seen in an algebra class before this. But just to remind you really quick, so when I write something like this, what I mean, so this is my sum symbol. And when I write something like this, I'm saying I'm going to sum, and notice for one, this is an infinite number of terms. But each term is going to look like 1 over n plus 3, and I just successively plug in n starting at 1, larger and larger. So this is not, it's not what it equals. It's not what the problem's asking, but just so you can see physically what I mean by this very efficient symbology here. What I mean by this is I'm trying to add together, so 1 plus 3 would be 4, so I'm trying to add together 1/4, and then 2 plus 3 would be 5, so that'd be 1/5. 3 plus 3 would be 6, 1/6, etc. And I'm going to add all of these up together, and there's an infinite number of them. So that's really with series that are infinite like this, that's really kind of the kicker as far as an idea, as far as a concept, is I'm saying that I'm going to add up 1/4, 1/5, 1/6, 1/7, 1/8, but I'm going to keep doing that, and I'm technically going to keep doing it infinitely. I'm never going to end the fractions that I'm going to keep adding to this. Now, what we're going to ask in this chapter, what this whole chapter is about, is ways to figure out this, does this sum actually add up to something? Does it converge? So their word for that is converge. But again, you were using that same word in the last section that we went over, 8.8. So remember in 8.8, we would do an integral. And remember an integral, right, it technically is kind of the same thing. An integral is adding up all the space under a curve, right? But we did integrals where one of our limits would go off to infinity, and we would ask the question, we try to figure out, does this integral converge or diverge? If it converged, that meant that there was an area, and so we would use the integral to get that area. And if it diverged, that means that when we tried to do that integral, we would get infinity, as usually infinity as a result, or we wouldn't be able to get rid of one of our infinities there, which means that, but what it meant was under that curve, that area just kept growing larger and larger, basically. So it kept growing infinitely. It never kind of topped out or tapped off at a certain value. So since infinite series are adding together an infinite number of elements, we have the same exact concepts. If the series converges, that means that when I keep adding these together, going out infinitely, at some place, somehow, those sums actually kind of top off or taper off. Whereas if it diverges, that means that the sum is going to keep growing infinitely. And so every problem in 9.3 through 9.6, and really this whole almost this whole chapter, is about figuring out, we're going to look at series and figure out, does it converge or diverge? Does the sum that I'm looking at, does it taper off somewhere and converge, or does it just keep growing infinite? So the question then is, how do we do that? And in section 9.3, they give you the first kind of test. So basically almost every section in this chapter is different tests, which are, what I mean by that is different ways we can tell whether these series are going to converge or diverge. And so the first test actually goes back to what we learned in 8.8. So I kind of keep referencing back to in 8.8, we figured out what do you call it? We did integrals that had an infinite boundary. And we figured out whether those integrals converge or diverge. And those integrals were sums. They're areas, but that's just the sum of a bunch of rectangles under a curve, right? So if we can figure out whether an integral converges or diverges, then there should be some relationship, or there should be some way to kind of port that over to figuring out whether these whether these series diverge, because both of them are sums. So the same action, the same concept, the same pattern should work for those. And so in 9.3, we're going to look at what's called the integration test. And the integration test is just what you did with infinite integrals ported right over to this. So the idea on this, I just, again, I just went through and started plugging in 1 and 2 and 3, etc., to give you the fractions that this corresponds to that we're adding together. But another way you can think of this term, or this term here is basically as a function. So not just that you can think of it, it is a function. So for every value of n, you plug in n and it spits out a fraction, and that fraction then is sort of the y value. It's the height, it's the amount for that function at that particular n value. So what I want you to imagine really quick, what we can do is we can imagine the graph of this function. So 1 over, let's say 1 over n plus 3. It's going to be a pretty easy one to graph. So let's say that's 1, then this will be 1, that'll be 2, that's 3, that's 4, that's 5, etc. So at 0, this is 1/3. In fact, I'm going to make this even larger. So let's say that's 1, then this will be 1/2, be quarter marks, etc. So at 0, this actually hits at 1/3, somewhere up here. And then at 1, this would be 1/4, and at 2, this would be 1/5, and then 1/6, and 1/7. And we can actually trace out a curve for that function here. So the way that we describe the series, in fact, is just a function. And if you think about it, then each of these fractions, for instance, this 1/4, like I said, again, that's your y value, that's your output at an n of 1. So you can think of this as then that value 1/4, it's as if you drew a rectangle right under the curve at that 1/4 mark. And then you could draw a rectangle underneath the 1/5 mark. And each of these rectangles, by the way, have a width of 1. So the area of this rectangle is 1/4 times 1, which is 1/4, and that's the first part of our series, first part of our sum. And the area of this second rectangle is 1/5 times 1, which is 1/5. So basically what I'm doing is I'm drawing rectangles underneath this curve that represents, the series. But these rectangles all represent what you're adding together to get this series. They represent each term of the series that you're adding together. So then I'd have a rectangle under here. And then I'd have a rectangle under here. Etc. So every one of these terms of the sequence is actually just a rectangle underneath the curve here. All right. So why am I kind of setting up all that? So again, a series is just a sum of all these terms. What I'm saying is all these terms are just rectangles underneath the respective curve that you would get if you graph that out as a function. And like I said, what we just got through in 8.8, I mean, I know it's a couple weeks ago, but what we just got through in 8.8 is we could figure out if this curve has an integral, if it converges, or if it doesn't have an integral, if it diverges. Notice that these rectangles, the area under these rectangles, just by nature, is, well, I'll ask you guys the question. So the area under those rectangles, is it less than the area underneath the curve, or is it more than? Or is it equal to? Good, it's less than the area under the curve. So notice that these rectangles, again, which represent the sum that you're getting from the series. So the sum from the series is less than the sum of the area. It's less than the area under the curve. So if this curve has an area under it, if it converges, then what should be true about the series, about the sum of those rectangles? Good, then they should converge too because they're less than. And if the, if the area under the curve diverges, then what should be true about the sum of those rectangles underneath the curve? It also should diverge, or at least we can't conclude that it converges. So what the integration test says is that instead of trying to add all these up, instead of trying to do some algebra and try to figure out some technique for adding these up and see if you can find, some limits to that sum, instead of that, turn this into an integral. So rewrite this as a function, integrate it from 1 to infinity, and if the integral converges, then the series has to converge. And if the integral doesn't converge, then the series doesn't converge. So in some sense, it's not only a simple test, but I think a really efficient and actually practical kind of simple idea. It just basically says the area that we're adding up, the sum that we're getting is less than whatever the sum is underneath the curve. So whatever the curve does, the series does. So the ultimate question for something like this, so number 3, they're asking, does this, actually, let me check. I'm sure they're asking this, but, yeah, so they're ultimately asking, does this converge or diverge? And so the way we're going to figure out is we're going to rewrite this as the integral from 1 to infinity of 1 over m plus 3. I guess that would be dn. And we're going to see whether this integral converges or diverges. So those skills that you guys learned in 8.8 now report directly into the beginning of this chapter. You'll see actually a lot of the skills that we've developed over the course. A lot of skills with integrals kind of come straight into this chapter. All right, so that's all we got to do. So let's do the integral on this. So I'll give you guys a second. What do you call it? I'll go ahead and pause on my side and you pause on your side. Go ahead and get the integral of this going and then check whether it converges or diverges. All right, let's see what you're getting. All right, so we're doing the integral of 1 over n plus 3 to the dn, and what is the integral of that? Okay, so the integral of that, this is going to be, so the integral of this is going to be the natural log of n plus 3, natural log of n plus 3, plus c, and we're going to evaluate that from 1 to infinity. All right, so when we do that, so what we're going to have is natural log of basically infinity minus natural log of 4. And the natural log of 4 is great, but the natural log of infinity just goes to infinity anyways. So since this goes to infinity, that means that the integral diverges. And if the integral diverges, then the series diverges. The sum of the series diverges. Good. So that's the heart of the integration test. Is it basically just says, well, a couple caveats here. So as long as your sequence, this is not just a caveat for the integration test. You'll see this is a caveat for almost all of our tests throughout this chapter, that the sequence or the series that you're looking at, the sequence for the series you're looking at has to be a decreasing sequence, kind of obvious for things. If I'm going to keep adding up a bunch of terms, if it's not decreasing, if things are kind of increasing, then of course it's going to be divergent. It's going to go out of bounds. But it has to be a decreasing sequence, kind of going one term after another. So every next term has to be less than the previous term. That's the heart of the requirements essentially. And obviously it has to be for the integration test, has to be something you can take an integral of. But so I sort of don't mention those conditions, those qualifications to begin with, because I think we understand naturally those qualifications just from the integral work that you're doing. So you obviously got to be able to take the integral. So yeah, pretty much the integral work itself will still basically, it'll tell you whether it converges or diverges. So you don't need to worry about the conditions a ton, except for the one condition is just making sure the sequence they're giving you has terms that are all less than the previous one, which is going to be true for the work in this book, because we want you to be able to evaluate the series that we're giving you. Good. All right. So, but again, that's the heart of the integral test. I guess I said integration, but it's the integral test. If you, what do you call it? If you do the integral and it converges, then the series converges. And if it diverges, then it diverges. So a good example really quick of one that does converge. Let's look at number 7 in that same exercise set. Number 7 is we're going to add together from 1 to infinity the terms e to the negative x. Make sure I got that right. Oh, e to the negative n. Get the variable right. And again, just to give you an idea, so what we mean here, so this is the series e to the negative 1 plus e to the negative 2 plus e to the negative 3, etc., which is a bit harder to imagine compared to the fractions we were just looking at on the previous one. But again, the beautiful thing with this integration test is I actually really don't need to be able to imagine what each of these terms look like, because the point of the integration test is if I can graph it, and then if I can integrate it and evaluate whether it converges or diverges for the graph, then that same result applies to the series. So if we can, and again, you don't need to see the graph, but remember that the graph of this then, so if this is 1, the graph of this looks like this, e to the negative x. So we're essentially trying to see, can we find the area underneath the curve? Because if this converges, then the rectangles that fit under it obviously are going to converge when you add them together. So, so again, what we're trying to find is, can we find the area from 1 to infinity of e to the negative n dn? Good. So then you see if you can integrate it and then see what your result comes up with when you integrate from 1 to infinity. So same idea. I'll pause really quick. You pause. Go ahead and see if you can do the integral there. All right, let's see what you get or what you got. So when you integrate this, so the integral of e to the negative n is going to be, that's going to be negative e to the negative n evaluated from 1 to infinity. Right. And dividing by the negative 1. Yes, good. And so that's when you start plugging stuff in there, you're going to have negative e to the negative infinity. And then minus a negative, so really plus e to the negative 1. And e to the negative infinity goes to 0. So this time we get the opposite result. That goes to 0, which means my definite integral here, my improper integral, does actually have a sum. The sum is e to the negative 1. So that means this converges. And again, as long as the integral converges, then the series converges. So again, all that work you guys did in 8.8 on those improper integrals, now this is actually, this is where it comes into play. This is why we did that. And conveniently, 8.8 comes really close right before chapter 9, right? So the author planned that out well. Good. All right, and that's 9.3. So 9.3 is just use the integration test. And things mimic each other. So if the integral converges, the series converges. If the integral diverges, the series diverges. In this section, you'll see they do mention something about the what's called a p-series and a harmonic series, but their little test for the p-series, or it's not even really a test, their summary about p-series, which is when these terms look like 1 over x raised to a power. Their summary of that is based on taking integrals, though. It's based on taking improper integrals. So the p test, or the p-series test, is just a subset of the integration test. It's just, they just applied the integration test to a set of what do you call it? A form, a set of series and sequences that have the same form. So I'm not going to teach that separately for you guys. So what I'm saying is the p-series is just the integration test. It's just the p-series. So if you read that in the section, you'll get a nice little summary based off the results from the integration test, but it is just the integration test. So for the p-series stuff in this chapter, feel free to read it and get that nice little summary, but also know that you actually don't need to know it at all, because in order to get that summary for the p-series, they did the integration test. So you could actually approach everything in this section by just doing the integration test, and you're still going to get the answer right. You don't need to know anything actually about the p-series. So do it whichever way you want to do it, but I'm just going to teach you guys the integration test because that gets you the whole section. All right. So let's look at then the next section and kind of the next test. Give me a second. So in 9.4, we pick up two more tests, two more ways to tell whether these series are convergent or divergent. And the reason that we need some other tests is because, so if you think about what we just did, so what we just did would work on a lot of series, but what if what if I write some series where the function, the function version of it is something that I can't easily integrate, or maybe can't integrate at all? So basically, that last test depended on integration. What happens when we can't? So we're going to need some other ways to kind of test whether these things converge or diverge. And so there, in this section, there are two different what do you call it? Two different ways, or yeah, two different methods that they introduced to kind of go about that. And again, specifically, so what we're trying to do is we're trying to look at scenarios where that integral is either maybe you can't do it, or it's just not as easily done. So for instance, this is number 10 out of 9.4. So this is the series, the sum from 1 to infinity. of 1 over the square root of n cubed plus 1. Right. And that's the first thing to go through, which we're not going to have time on this video, but you can pause and go through it yourself. The first thing you want to go through then is kind of convince yourself that this is a hard integral that maybe we can't do, or just something that's really hard to do. And so this honestly would be. So the integral on this would look like 1 to infinity of that same thing, really. But the problem there is these little square root forms are notoriously kind of hard to deal with as far as integrals. They often end up as like inverse trig ratios or something like that. And this isn't even one of the nice ones that ends up as an inverse trig ratio. So as an integral, this is something that just really can't be done. So if it can't be done, then we're kind of back to square one. What do we do with this? So the first test from this section is called the direct comparison test. And again, let me talk really quick about the idea behind this test. But it's a really clever little test, actually. So what I want to do is really just kind of over here really quick. Let's say that so I'm gonna basically graph out a series. Well, yeah, I'm gonna graph out the sequence of a series. So let's say this is the sequence that kind of underlines some series that we have. And let's say that this sequence is convergent. Then here's my question to you. So let's say, so this is, again, these are each of the elements in the sequence that makes up my series, the pieces that I'm adding together. So we'll call this sequence AN. What if I have another sequence that's less, that each what do you call it? Each part of, yeah, each element of that sequence is less than the one that I'm seeing for the convergent sequence. So let's say that one's there, and this one's there, and maybe that one's here, etc. But they're all less. And so we'll call this Bn. But if all of these are less, and the larger sequence or the larger series is convergent, then what has to be true about something that's smaller than that? Good, it would have to be convergent. There's a good bit of just, honestly, just geometry logic here. That if I have some shape here and the area under that can be found, and then I have some shape underneath that that's smaller, then surely the area for that can be found. So if the larger, and what I mean by when I say larger, what I mean is each of the terms that I'm looking at in this series. If the larger series is convergent, then surely one smaller than that has to be convergent. So this is where we kind of get the name direct comparison. So what we're going to do with the direct comparison test is, instead of trying to integrate this, which we know is impossible, we're going to make another sequence that's intentionally maybe less than, each element of the sequence is less than the one we have in 10. Or no, so I'm sorry, greater than. Maybe make one where it's greater than. And if that series is convergent, so if I can make a series where each element, each step along the way is bigger than the one I see in 10, and the bigger series is convergent, then 10 has to be convergent. Now, one thing I want to mention here then, let's say this bigger series is divergent. And I'm comparing it to a smaller series. Then does that make the smaller series divergent? And the answer is not necessarily. So this smaller series could be small enough that its sum actually does converge. And we won't know that because this bigger series, again, so I think of the bigger series almost like an umbrella, like what do you call it? Like it's containing the smaller one. If the bigger one is divergent, it just means that this sum, as you go out to infinity, never settles down. But this smaller one could be small enough that it does settle down. So if you have a bigger series and a smaller series, if you know the bigger series is convergent, you know the smaller series is convergent. But if the bigger series is divergent, then that doesn't tell us anything about the smaller series. However, again, let's say we're starting with series AN and this time it's divergent. What if I make a series bigger than AN? So what if I make all my pieces for B of BN bigger than the ones I see for AN? What if this is BN? And if I already know that AN is divergent and AN is actually smaller than BN, then if this is divergent, what has to be true about BN? Good, BN has to be divergent. So if something smaller is divergent, then surely the thing with the bigger area then also has to be divergent because it's more. And again, divergent just means that the sum never settles down. It goes to infinity. So what's more than infinity? Nothing. So the only way to have more than infinity is to have more infinities, to have infinity. So if I know that a smaller series is divergent and I compare it to a larger series, I know the larger series is divergent. So those two definite parts of the result are actually, those are the comparison tests. So the direct comparison test says that if I have two series, or really sequences, but well, okay. I don't want to repeat too many words here, especially because I don't have the time. But if I have two sequences, AN and B sub N, but basically you have two conditions here. If AN is less than or equal to BN, well, okay, yeah, we'll just say this, and the sum on AN diverges. So if the smaller one diverges, then the bigger one diverges. That's really the way I remember it, honestly. Then if the reverse, so if in fact AN is greater than or equal to BN, and AN converges, so if the bigger one converges, then the smaller one converges. I don't like the way that's written, but hopefully you guys kind of get the idea there. All right. So that's what they call the direct comparison test. So if a bigger sequence or series converges, the smaller one does. And if a smaller series diverges, then the bigger one does. So with that in mind, then if we want to solve something like 10, we want to figure out, does that converge or diverge? What we have to do is so first of all, we have to sort of make a guess on maybe whether it does or it doesn't. And based on that guess, we need to make another series. Basically, we need to make a simpler function that we know already, or at least we can test that it converges or diverges. So that's kind of the heart of the issue here. When we went to do the integral of this, we realized this function is too complicated. So our first instinct is we need to make a simpler function. And then that simpler function has to be, we're going to try to make it so the elements of that function are either always bigger or always smaller than the one we have there. So for instance, what I would do with this. So this is too complicated. If I could just strip off this +1, in fact, I know why it's too complicated. It's this +1. And if I could get rid of the +1, 1 over n cubed, the square root of n cubed, that's actually just a power function. That's really easy to integrate. So I'm gonna take off the +1 here, but when I take off the +1, I gotta kind of note in my mind, what does that do to each of these terms? Does it make them smaller or larger? So kind of think this through with me. So if I'm doing 1 over n cubed, square root of n cubed +1, if I don't add 1, so if I'm doing 1 over, so let me write it out. So I want to look at a second sequence. This sequence is just gonna be the square root of n cubed. Now, first off, the pieces here, calculation wise, are they going to be smaller or larger than what we have than the one we started with? So by adding 1 in the bottom here, what this does is it makes the bottom of this fraction a little larger. And if the bottom of the fraction is a little larger, what does that do to my fraction? It makes it a little smaller, right? So what I'm saying is basically this is always less than, at least less than or equal. But I think it'll actually just be strictly less than. It's always less than 1 to infinity of 1 over square root of n cubed. But this is the simpler one to take an integral of, right? So what I'm going to do from here is, in this case, the bigger series is something that I can figure out whether it converges or diverges pretty easily. So I'm going to figure out what happens with the bigger series. And then what I'm hoping for is that it converges, because like we just kind of went through, if the bigger one converges, then the smaller one converges. So I'm hoping that works. Let's see if it does. So now what we have to do is we have to figure out, does 1 over the square root of n cubed, does that converge or diverge? And to do that, you're going to do your integration test. First, let's figure out what happens here. Integral from 1 to infinity, 1 over the square root of n cubed dn. All right, so I'll go ahead and pause. You pause, take a second and figure out whether that converges or diverges. All right, so then for this integral, notice that this is actually basically n to the -3/2 power. So the integral of this is then going to be what, n to the -3/2. So it's going to be -2 n to the -1/2, evaluated from 1 to infinity. And actually, just for the sake of, let's actually write that out. So this would be -2 over the square root of n is what we're trying to say there, from 1 to infinity. Just making sure that was good. And then that would be, well, that would be -2 over the square root of infinity. then plus, so minus a minus plus 2 over the square root of 1. This goes to 0. And so this does in fact equal a number, which tells us that it converges. So this converges. And this is the bigger sequence, which means our smaller sequence that we started with has to also converge. And that is the direct comparison test. At our next. All right, so to give you guys an example of sort of the opposite there. So I think this is actually one of the earlier exercises. Seven. And 7 is the sum from 1 to infinity of 1 over the square root of n minus 1. And this actually, I was actually for a minute when I looked at it earlier, I was like, no, you can find the integral of that. But this is another one that looks surprisingly simple, but you actually is really hard to find the integral of. So if you just translated this into the integration test, you kind of be stuck spinning your wheels for a while. So instead, what I'm going to do is kind of similar to the last one. I'm basically going to simplify this by taking off the minus 1. But this time, when you take off the minus 1, if you think about it, minus 1 is going to make the bottom smaller, right? Which for a fraction, if the bottom is smaller, the overall value is larger. So this is automatically greater than the sum, not just the sum, but every element's going to be greater than 1 over the square root of n. So again, kind of opposite situation where the one that we're trying to find, I set up another sequence, simpler sequence, one that I can actually do some work on. But this one is always less than the one that I'm starting with, or the one that I'm starting with is greater than the one that I created. All right, so let's do our work on this then. And so this, I mean, again, feel free to pause and do this work yourself, but for sake of time, let me go ahead and start working through this. All right. Sorry. So I'm going to do the integral now from 1 to infinity of 1 over the square root of n, but I can rewrite that as n to the negative 1/2. And the integral of that is then going to be 2 n to the 1/2. We're going to evaluate that from 1 to infinity. And if you look at that, this is definitely going to give us issues. So basically, this is going to be 2 times the square root of infinity minus 2 times the square root of 1, so minus a 2. But that does not go to 0. That goes to infinity. So this series that I created diverges, and this series is always smaller than the series that the series that I'm looking at. So if something smaller diverges, what has to be true about the larger? It also diverges. Good. So these are the two kind of scenarios. These are the two scenarios where the direct comparison test tells you something. So again, if either of these were reversed, it wouldn't work. So for instance, on 10, if my larger series was divergent, I actually can't tell if the smaller series is divergent. And vice versa on 7, if my smaller series converges, then I definitely can't tell if the larger one converges. So it's only these particular combinations. So that's your direct comparison test. In this section, they also have another comparison test called the limit comparison test. So let me pick a problem and then just kind of meander through, just kind of give you guys an explanation for why we might use the limit, why we need another tool, basically. So when this comes in handy. All right, so let me write up a problem. Try to do these as quick as possible. So it's limit comparison test. We're going to look at 19 to start with for this. So the idea of the limit comparison test, again, we're going to be looking at things that, first of all, hard to take integrals of, so you can't use the integration comparison test. Limit comparison test is helpful when you can't I guess then for series where you can't naturally think of another series that's either greater than or less than it, but not necessarily even that. So let me write 19 down. And we'll look at what we can do with this. So this is the sum from 1 to infinity. 1 over the square root of n squared plus 1. Now, again, going back to the integration test, this is going to be a mess. I actually think that plays out as a inverse trig ratio, but that still becomes a mess as far as integration. So that's not nice. Now, looking at the last thing we did, though, the direct comparison test, we could try to do direct comparison tests with this. So I intentionally wanted to do one that you could do direct comparison tests with this. But we can also do something called the limit comparison test. And so the idea with the limit comparison test is just like the direct comparison test, you're going to make another simpler series right beside this one. But instead of comparing them, so instead of worrying about one being less, one being greater than the greater being convergent or the less being divergent, etc. What we're going to do is we're going to take the limits of basically the more complicated series divided by the the less complicated one. So the limit comparison test is about actually doing a limit of one series divided by another. And based on the result of that limit, we'll be able to tell basically whether these series converge or diverge. And so the limit comparison test, just like these other tests that you've seen, basically your results are always in tandem. So if we get a result that tells us it's convergent, that means both of those series converge. And if we get a result that says it's divergent, both of those series diverge. So they either both do one thing. They either both converge or they both diverge. But we're going to do this now not with integrals. So the big difference with this one is we're not going to do this with integrals at all. We're going to do it with limits. So I look at this, and obviously the thing that's making this complicated is the plus one. So if I take the plus one away, again, what I'm going to do is I'm not going to be worried about less than or greater than. But if I take the plus one away, notice that the square root of n squared, what is that? That's just n. So I'm going to basically compare this. I'm going to compare this series to the series 1 to infinity of just 1 over n. So just the results you get on this after you take away the plus 1. You end up with 1 over n. So what I'm going to do, I'm literally going to take the limit as n approaches infinity of the series that I want information about divided by series that what do you call it? That we know some information about, or at least the simpler series. So I'm going to take 1 over square root of n squared plus 1, and I'm going to divide this by 1 over n. So this is why they call it the limit comparison test. You're taking a limit, but you're comparing these two functions, and by compare, they really just mean divide. And so what this does is this takes your work back to, now you're actually not even doing integrals. This takes you back to like chapter 2 of calculus 1. This is just pure from here. This is just pure algebra and limit work. So when I divide, that means this gets flipped over. So what I end up with is the limits as n approaches infinity of, it's going to end up being 1 over n is going to flip, and then you'll multiply, so you'll end up with n over the square root of n squared plus 1. So what this does mean is now you got to remember some of those algebra techniques you use to do limits out of chapter 2 of the calculus book. I use usually chapter 2, something like that. So one of our techniques here, I'm going to change the top to the square root of n squared. Well, I mean, it's yeah, sure. And this will be square root of n squared plus 1, which means I can combine these into one gigantor square root, where it's n squared over n squared plus 1. And then I'm going to divide each of these down by n squared. Divide everything down by n squared. So again, hopefully this rings some bells from your first calculus class, but this is kind of the official algebra that you would keep doing here. So I'm going to divide everything down by n squared so that I can get pieces that when I plug infinity in, I either get a number or I get 0 or something like that. So I'm going to end up with 1 over 1 plus 1 over n squared. And then when I plug infinity in, what I end up with here second. Actually, wait, hold on. This is not supposed to converge. Second, I think I did some algebra wrong here. Supposed to get to a point where you don't have infinity divided by infinity. So why I'm messing up because I need to supposed to be done with this already. Actually, I can't just, that's where I'm wrong. I can't just divide this by n squared. Yeah, sorry. That was wrong algebra there. Yeah, well, pretty much we're just not gonna get anything else out of this other than replacing n in this. And when you replace, replacing n with infinity. So what I end up with here is the square root of infinity, which equals infinity. And so if my limit goes to infinity, that means, like we've seen every time, if the limit goes to infinity, that means that this diverges. So this means it diverges. And like I said, the idea here is these work in tandem. So this just tells you essentially what the result is for both. So both of these series diverge. So they either both diverge or they both converge. So this is only going to converge then if your limit actually comes out as a solid number. So if it comes out as a solid number, then you've got it. It converges. And that's the limit comparison test. So form an easier series and then divide one by the other. And take the limit as n approaches infinity of that division. And the limit will tell you. So if it goes to infinity, it diverges. If it goes to a solid number, it converges. Good. All right. So what I'm going to do is I'm going to have you guys read through and kind of finish up 9.5 and 9.6. So 9.5 and 9.6 though give you a couple more what do you call it? A couple more types of what do you call it? Sorry. Tests for convergence or divergence, but they're useful in very specific circumstances. So they're definitely useful in those sections because they designed those sections to be about those limit tests. About those convergence and divergence tests. But in general, you'll see from some of the examples in 9.5 and 9.6 that the types of series, that the form of the elements that you have in your sequence are very specific. But you'll see again in 9.5 and 9.6 that whatever tests you're using, so the tests are in 9.5 you're gonna learn the alternating series tests, and then in 9.6 you're gonna need to learn the ratio and the root tests. But just like in 9.3 and 9.4, whatever tests you're using, your results always work in tandem. So they're either both convergent or they're both divergent. And that's really the biggest lesson to learn from these four sections then. So whatever tests you're using, that holds true the whole time through. They're either both convergent or they're both divergent. And that's how we can tell that these series are convergent or divergent, is we're always comparing them to something else. So with the integral test, we compared it to a function that we could integrate. With the direct comparison test, we physically created a whole nother series that we could compare it to, right? With the limit comparison test, you're again doing that. You're creating another series that you can compare it to. So you'll see, even with the alternating test and the ratio and root test, you're comparing it to another series, and either they're both convergent or they're both divergent. Okay. So, and again, I'm sorry, guys. I would have had another hour to make this video, but the room that I made videos in doesn't exist anymore, basically. So I had to kind of scramble around for an hour and figure out where I was going to make this video. But you guys can easily work through 9.5 and 9.6. So just read those sections, take a look at their examples, and then work the homework. And then I will be back in this room another time to give you guys a review for the final next Wednesday. See y'all then.